Hi, welcome back to the online session. In this session, we will discuss about single source shortest path problem. This problem will be solved by using dynamic programming algorithm design technique. And there is another name called as Bellman-Ford algorithm. Students, both are same. Single source shortest path problem or Bellman-Ford algorithm, both are to be considered as same. Here, if you observe clearly, the single source shortest path problem already we have been solved in earlier unit, that is unit 3. The single source shortest path problem can be solved by using Dijkstra algorithm in previous unit, unit 3, that is based on the principle of greedy method. So, observe the difference clearly. The single source shortest path problem can be solved by using two ways. The first one is using Dijkstra algorithm that can be solved by using the principle of greedy method. Here in this session, the same single source shortest path problem can be solved by using another method that is called dynamic programming method by using the algorithm name is Bellman-Ford algorithm. It seems to be the same problem, single source shortest path problem can be solved by using two different techniques, namely 3D method and as well as dynamic programming technique also. In greedy method, we use the algorithm called Dijkstra algorithm, whereas in dynamic programming, the problem can be solved by using Bellman-Ford algorithm. But here, we need to compare the difference between the dynamic programming technique and greedy technique, how those the impact will be held in single source shortest path solve solution. Students, while we are using Bellman-Ford algorithm in this session is because Bellman-Ford algorithm computes shortest path from a single source of vertex to all the remaining vertices in a weighted directed graph. And also, the algorithm is used to find the shortest path. Another algorithm is we are using instead of Bellman-Ford, that is called as a Dijkstra algorithm. That means that the single source shortest path problem can be solved by using two algorithms, namely one is Bellman-Ford algorithm and another one is Dijkstra algorithm. The single source shortest path problem can be solved by using Dijkstra algorithm and as well as another one is Bellman-Ford algorithm. The Dijkstra algorithm we can solve the problem by using greedy technique. By using greedy technique, we will solve the problem. But whereas the Bellman-Ford algorithm can be solved by using the technique that is called as DP, stands for dynamic programming. And what is the difference between Dijkstra algorithm and Bellman-Ford algorithm, while solving the shortest path problem, we will see clearly in this section. Okay. Here, the Bellman-Ford algorithm is more versatile if you compare to the Dijkstra. Why Bellman-Ford is more versatile is it is capable for handling the graph in which some of the edges weights are negative numbers. That means that the Bellman-Ford algorithm or the dynamic programming technique can be used to solve single shortest path problem. Even the graph can contain negative edges. But in Dijkstra algorithm cannot be support for solving the graph can contains negative edges. That is the main difference between both Bellman-Ford algorithm as well as Dijkstra algorithm. If you consider this is the graph can contains the negative edge is the negative edge for A to B is minus 3 and this is the positive edge. These three are positive edge. That means that the graph can contains one negative edge and three positive edges. The negative edge and the positive edge can be combined in the given graph. The graph can be solved in the graph can be solved by using Bellman-Ford algorithm only. The graph cannot be solved by using Dijkstra algorithm. Why? Because Dijkstra algorithm cannot support for solving negative edges graph. So that is the one of the drawback of Dijkstra algorithm. Bellman-Ford algorithm is used to solve single shortest path problem in the given edges of weights may be negative, but no negative cycle exists. Very, very important term. Bellman-Ford algorithm can be used to find the single shortest problem of the given graph. The graph can contain negative edges, it can be worked, and the graph cannot contain negative cycles. That means that if the given graph can contain negative cycles, then in this case, Bellman-Ford algorithm cannot be supported. So hence, while solving or before solving Bellman-Ford algorithm, you need to check or ensure that the given graph cannot contain any negative cycle edges, any negative cycle edges. But it can be support negative edges. Negative edges can be support. But cycles cannot be formed. Cycle in the sense, the graph, if you consider any three edges, the cycle should not be formed in the graph. So cycle cannot be entertained in the Bellman-Ford algorithm. And the second point is the Bellman-Ford algorithm works correctly when some of the edges of the directed graph may have negative edges. That means that this is the one of the advantage of Bellman-Ford algorithm. We can solve the given graph by using Bellman-Ford algorithm to find the shortest path. Even the graph can contain negative weights. When there are no cycles of negative weights, then we can find out the shortest path between source and destination. That means that when the problem can be solved is no cycle of negative weights are formed. That means that cycle cannot be formed in the given graph. The problem can be able to solve by using Bellman-Ford algorithm. And one of the drawback of Bellman-Ford algorithm is it is slower than Dijkstra algorithm. The Bellman-Ford algorithm is slower than compared to Dijkstra algorithm, but the positive concept is it is more versatile as it is capable for handling negative edges. So these are the differences between Bellman code algorithm as well as Dijkstra algorithm, right? Next we will see where exactly Bellman Ford's algorithm cannot be solved. We will see in this slide. Here, consider this is the graph. Consider that this is the graph. In the graph, this is considered as connected directed graph, directed weighted graph. So directions are there, and the there is a weight from one node to another node. The weight from node A to node B is 2. The weight from node B to node B is 1. Here, if you consider this part, if you observe this part, here cycle is formed. Cycle is formed in this area. How cycle will be formed in this area, you can clearly observe that there is a cycle formed here. If you observe clearly, B to C, C to D, and D to B. B to C, C to D, and D to B. That means that cycle is to be formed here. Cycle is to be formed here. I will tell you clearly. Uh, Clearly, I will tell you. If you consider this part, in this part, B to C, C to D, and D to B. Cycle is to be formed. Cycle is to be formed here. Consider this part. B to C, there is a direction. C to D, there is a path. And D to A, there is a path. That means that cycle is formed here. Cycle is formed here. Cycle is generated here. Hence, this graph cannot be solved by using Bellman Ford algorithm. So cycle is generated here. Hence, this graph cannot be solved by using Bellman Ford algorithm. So, friends, observe clearly in examination also. If this type of problem wants to solve, this cannot be solvable. This type of problems cannot be solvable. Why? Because in the given graph, cycle is formed with the negative edges. Cycle is generated with the negative edges. Here there is a negative edge. C to D, there is a negative edge. That's why C to D vertex C to D negative edge is formed along is formed. So here we clearly observe that here vertex C to D, if you observe here, negative edge is formed and also cycle also generated. So the main concept is cycle should not be formed with negative edges. Cycle should not be formed with negative edges. But here cycle will be formed with negative edges. That's why this problem is not considered for solving by using single source shortest path problem. Okay. Next, we will discuss about where exactly single source shortest path is used in real-time example. Now consider Google Map. This is one of the application. In Google Map, we may use Bellman code algorithm for finding the shortest path between two different locations. If you observe the graph here, this is the map. In this map, consider the map as a graph. The map, if you consider this is a graph, why? Because there are number of vertices and the vertices are connected through directly or indirectly through edges, and the distance between from one edge to another edge is also mentioned. So here we need to consider the given map as a graph, and the locations in the map are vertices. The locations in the map are called as a vertices. So consider this is the source vertex and this is the destination vertex, and there is a path exists from source vertex to destination vertex that is called edges, and with a total distance is mentioned that is called as a weight. So here roads and road length between the locations are considered as a edges and weights. So this is one of the real-time example for single source shortest path. So where exactly single source shortest path is applicable in the real-time example, in the sense if we want to travel from source city to a destination city, you have a direct path or you need to go through the intermediate cities. But finally, always remember that you need to find the shortest route or path from your source to the destination that will be considered as the optimal solution for the given problem. So in this way, this single source shortest problem can be solved. Next, we will talk about another example, telephone networks. If you observe the telephone networks, the lines have bandwidth. Bandwidth in the sense the speed of the network. If you want to route, if you want to route the phone call through high bandwidth and consider the transmission lines with highest bandwidth as the shortest path. So here, if you want to establish a well qualified telephone network among different cities through the connected mode, here this problem will be very useful for designing the single source shortest path to cover all the cities. So why? Because if you consider the graph, telephone networks is to be considered as a graph. In the telephone network, there are switches of the switch stations we can consider as a vertices, and also some transmission lines to be connected to the network. Those transmission lines are to be considered as the edges, which can be connected to two switching stations. The transmission lines are used to connect two switching net station networks. So those are considered as vertices and edges. And the bandwidth in the network is to be considered as the weight. So some one switch station to another switch station, so there is a bandwidth. The bandwidth can be considered in the terms of weights. So in this way, we can consider many examples for single source shortest path. Students, listen carefully how to solve single source shortest path problem by using Bellman code algorithm through the concept of dynamic programming we will see. Now we are solving the given problem by using dynamic programming only. Now we will see how to do that. We will solve the problem by using dynamic programming. How to solve the problem we will see here. So this is the given example. The problem can be solved by using dynamic programming technique. So in the if you want to solve dynamic programming, so the first thing is Bellman Ford algorithm you need to use it. to solve the problem. If you want to solve the problem by using dynamic programming technique, you use Bellman-Ford algorithm. The Bellman-Ford algorithm can support for negative edges. Negative edges. Even if the given graph can contains negative edges, it is supported. There are some negative edges, namely 2 to 3, there is a negative edge, and 3 to 2 there is a negative edge, and 4 to 3 there is a negative edge, 4 to 6 there is a negative edges. Negative edges also it is found, but it cannot work when negative cycle is formed in the graph. The graph. Now consider the given graph. Any negative edges are found or not? There are no negative edges. Negative edges are there, but negative cycles is not formed. Negative cycle is not formed in the given graph. That's why we can able to solve the problem very quickly by using the concept of dynamic programming. So it seems to be we can solve the problem by using dynamic programming concept only. Okay. Now we'll see how to solve the problem. Now we will see how to solve the problem. Before solving the problem, before solving the problem, we will consider one formula. The formula is relaxation property. Relaxation property. Consider this is U and this is V. This is U, this is V. Node V, node V, node U. The relaxation property is if distance of U, distance of U is, the distance of U is initially 0. That means that 1 to 1. What is the distance from 1 to 1? The distance from 1 to 1 is 0. Distance of U is considered as 0 plus cost from U to V, the cost from vertex U to V. The cost from vertex U to V clearly describes the path from U to V. The path from U to V is 6. The path from U to V is 6. Simply you can add this to the sum. You can add this to the sum, that is compared with D of V. D of V, initially the distance from vertex 1 to vertex 2 you don't know, that's why you can consider this is infinity. The distance from the distance of V, so distance of V we don't know. D stands for distance of V. The distance of vertex 2 you don't know, that's why you can consider it is infinity. Now clearly observe that 0 plus 6 is less than to the infinity. If the condition is true, in this case d of v, distance of v is considered as d of u. The d of u is here. What is d of u? D of u is 0. D of u is 0, 0 plus cost from u to v. Cost from u to v, cost is 6. 6. So total is 6. D of v is 6. Now the cost of d of v is 6. Now the value of d of v infinity is replaced with 6. The cost of d of v is replaced with 6. In this way, we can find the minimum cost path from one vertex to another vertex clearly. I hope you understood this. Okay. Now we will move to another slide here. Move to another slide. So here, this is another slide. In this slide, we already written a relaxation property Relaxation property, this is the relaxation property. We need to apply relaxation property to the given graph. Before solving the graph, we need to generate, we need to generate the edge list from the given graph. The possible way of edge list from the given graph, we need to generate here. So based on the directions, we need to generate the edge list. How to generate the edge list? These are the edge list which can be generated from the given graph. Observe, observe the directions clearly. If you consider the first vertex, vertex 1, and if you observe here, there is a path from 1 to 2 directly. 1 to 2, there is a edge. So this is the edge 1 to 2. Next edge is, if you observe here, there is one more possible edge is 1, 2, 3. This is another edge which can be generated. And one more edge is 1, 2, 4. This is another edge. So from vertex 1, there are 3 edges are to be generated. And from vertex 2, how many edges are generated? From vertex 2, what are the out edges? Out edge is only one, that is vertex 2 to vertex 5. So that is 2 to 5 is the edge which can be generated. And there is no possibility 2 to 3 also no possibility. Why? Because there is no direct path from 2 to 3. So simply ignore it. Next, move to third vertex. So if you consider the vertex 3, so what are the ways we can move from vertex 3 to vertex 5? There is a direct path. So 3 to 5 is a direct path, and 3 to 2 also there is a path. 3 to 2 there is a direct path. You can consider this one also. And the next path is 4 to 3. Next is, if you want to consider the vertex 4, there is a direct path exists from 4 to 3. So 4 to 3 is considered as another edge. And 4 to 6 also, there is a path, direct path. 4 to 6 is also considered as another edge. And 5 to 7, this is the destination vertex, 7 is the destination vertex. Vertex 5 to vertex 7, there is a edge generated. Vertex 6 to vertex 7, there is another edge is to be generated. And total 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 edges are generated from the given graph based on the directions while moving from source vertex 1 to destination vertex 7. This is 1 is source vertex and 7 is the destination vertex. Students observe clearly when in examinations they are given the given graph, they are asking solve the given graph by using single source shortest path problem or Bellman 4 problem using dynamic programming. The first step is from the given graph, you need to generate the possible edge list. You need to generate all possible edge list. So these are the possible edge list which can be generated based on the directions from the given graph from one vertex to the source vertex to the all remaining vertices. Okay. Next, you need to write the relaxation property. Relaxation property in the sense here there is a C stands for cost and D stands for distance. Cost of u comma b, u is one edge, u is one edge, sorry, u is one vertex and v is another vertex. U is one vertex and v is another vertex. Cost of u comma v in the sense path. Cost of u comma v in the sense path from 1 to 2. It is path cost of u comma v in the sense path from vertex path of u to v. That is 6 here you can generate. And the distance of u, the self distance, what is the distance of 1 to 1? The distance of 1 to 1 is 0. And we don't know the distance of v. We don't know the distance of v. That's why we can consider the distance of v is considered as infinity. Now you can sum these two, 0 plus 6, you will get 6. 6 is less than infinity, then in this case we will get the value is 6. 6 is replaced, the infinity is replaced by 6. So in the first step we got the minimum cost from 1 to 2. Okay, so in this way we will do the problem, and in the same way we will do the same problem in multiple ways. Okay, next step is next step is clearly observed here. Clearly observed here. If you compare, if you compare this graph with this graph, clearly observed here, the weights of vertex 2, vertex 3, vertex 4, vertex 5, vertex 6, vertex 7 are not given. But here, if you observed here clearly, if you observed here clearly, just a minute. If you observe clearly, the first vertex distance is 0. Source vertex distance we can consider as 0. And the all remaining vertices cost you can consider as infinity. This is infinity. And this is also considered as infinity. And the cost of this is infinity. 7 vertex cost is infinity. Vertex 8 cost is infinity. And assign the first vertex cost is 0, and the remaining vertices cost you can assign as infinity. This is the first step. Okay, okay, you understood that. Okay, here, what are the total number of ways you can do is this is the source one, and this is the destination one. This is the next step. Once the first vertex is assigned 0 cost, and the remaining vertices we can assign the cost is infinity. Why? Because initially we don't know that cost. That's why simply use that one. Okay, this is the second step. Next step is so this is the next step. Clearly observe here. This is the next step. How we will do is once the first edge once so this is the first edge. The first edge cost is 0. Now apply relaxation formula to the given graph. Apply relaxation formula to the given graph. So now I am applying relaxation formula to vertex 1. If I apply relaxation formula to vertex 1, distance of u is 0 plus cost of u to v. Cost of u to v is 0 plus 6. Cost of u to v is 0 plus 6, that is called 6. And the distance of v is, this is considered as u, and this is considered as v. You simply apply this. The cost from 1 to 2 is, you simply add 0 plus 6. The 0 plus 6 is less than to the infinity. 0 plus 6 is less than to the infinity. So infinity is replaced by 6 here. Okay. Once again, I will explain. Now consider the edge list here. These are the edge lists. Now you can consider the edge list. First consider the edge 1 to 2. First consider the edge 1 to 2. Consider the edge 1 to 2. So if you consider the edge 1, vertex 1 to vertex 2, if you consider this edge, this is the edge if you consider initially, if you consider that, apply relaxation formula to this. Distance of u is 0, and cost of u comma v, the cost of u to v is 0 plus 6, 6. And the distance of v is infinity. The distance of v is infinity. Now compare 0 plus 6. 6 is less than infinity. The condition is true. Then the d of u plus c of v cost is 6, and here d of v is 6. That means that 6 equal to infinity. That means that infinity is replaced with 6. So infinity is replaced with the value of 6 here. Okay, this is the first step. Next, consider 1, 2, 3. 1, 2, 3, if you consider 1, 2, 3, which one is the minimum value? So here we cannot mark it here. This is also infinity. The distance from the cost of 3 is infinity. If you consider 1, 2, 3, 8, if you consider 1, 2, 3, 8, here the cost of, now you can consider the same here. The cost of the edge is here 0 plus 5. So if you consider 5 with infinity value, which one is smaller? The the distance from one, the path from 1 to 3, the path from 1 to 3, if you consider the edge 1 to 3, what is the total cost from 1 to 3 is, total cost from 1 to 3 is 0 plus 5. So total cost is 5. Now compare 5 with infinity value, which one is smaller, you can consider. 5 is smaller, so infinity is replaced with the value of 5 here. So second also 1, 3 edge also completed. Next you move to another edge. The edge is 1 to 4. Now here you can consider another edge 1 to edge 4. Here there is a path exists from vertex 1 to vertex 4. Now you need to find the minimum cost here. So if you consider here, there is a direct path from 1 to 4 of cost 5. And what is the total cost is 0 plus 5. Total cost is 0 plus 5. And here the weight of 4 is infinity. Which one is smaller? 5 is smaller. So infinity is replaced with the total cost of 5. Okay. Next, you can consider the edge 2 to 5. If you consider the edge 2 to 5, if you consider the edge 2 to 5, so what is the distance from 2 to 5? The distance from 2 to 5, you don't know, that's why infinity you can consider. But the distance from 2 to 5 is 6 minus 1. So the distance of 2 is 6, and the distance from the you simply apply this formula. So 6 minus 1, 5. If you can consider 5 compared with infinity, which one is minimum is 5 is minimum. So infinity is replaced with 5. Next 3 to 2, you can consider the edge 3 to 2. 3 to 2, you can consider edge. If you consider the edge 3 to 2, the minimum cost from 3 to 2 edge is already the edge 3 is 5. 5 minus 2. 5 minus 2 is 3. So here 6 is there. 6 is again replaced with minimum value is 3. Next, compare 3 to 5. Compare the edge 3 to 5. Here the edge is 3, 3 to 5. You need to find the minimum cost distance from 3 to 5. So the minimum cost distance from 3 to 5 is 5 plus 1, 6. If you compare 6 with 3, 3 is minimum. If you compare 5 plus 1 is 6. If you compare 6 with 3, sorry, not 3, compare 6 with 5. Compare 6 with 5. Which one is minimum? 5 is minimum. Then there is no change exist. Next, 4 to 3. You can consider 4 to 3. 4 to 3, if you consider the minimum cost, you need to find here. The vertex 4 is having 4 to 5. If you consider 5 minus 2, cost is 5 minus 2, 2. The cost is 2. Sorry, 5 minus 2, the cost is 3. Now compare 3 with 5. Which one is minimum? 3 is minimum. So 5 is replaced with the value here. Next 4 to 6. Next 4 to 6 you can consider. 4 to 6 if you consider, find the minimum cost path. And the cost is 5 minus 1, 4. 4 compared with infinity. 4 is small. So infinity is replaced by 4. Next 5 to 7 edge list. 5 to 7 edge list. If you compare 5 to 7 edge list here, the minimum cost is 5 plus 3, 8. Compare 8 with infinity. 8 is small. So hence you can replace infinity with 8. Next 6 to 7, edge 6 to edge 7, if you consider the minimum cost path is 4 plus 3, 4 plus 3, compare 4 plus 3, the value is 7, 7 compare with the value here, the value is 8, 4 plus 3 is 7, 7 is smaller than 8, hence 8 is replaced with 7 here. So this is the pass 1, this is considered as a pass 1. PASS. Pass 1 is completed. Pass 1 is nothing but first full cycle is to be completed. But how many number of times we need to do this is we need to do the problem in how many ways, that is called as a v minus 1 times we can do it. V is number of vertices minus 1 times we need to it. So here the number of, sorry, not number of vertices, the total levels minus 1. The level 1 is, this is level 1, level 2, level 3, level 4. There are 4 levels. First level, second level, third level, fourth level. 4 minus 1 times we need to solve the given problem. Okay, 3 times or 4 times we need to solve the given problem. So this is the first way. Now at the end of pass 1, at the end of pass 1, we are getting the minimum cost path from one edge to another edge in this clearly observed here. So this is the end of pass 1, and again you can apply the same concept to the given graph. Apply the same concept to the given graph. Now here you can consider the first path 1 to 2. If you consider the path from 1 to 2, what is the total weight? The cost is from 1 to 2, the total weight is 0 plus 6. 0 plus 6, 1 to 2. If you consider here, if you want to consider the path from 1 to 2 here, the total cost is 0 plus 6. Compare 6 with 3. 3 is small, so no change is occurred. 1 to 3 edge you can consider. If we consider the edge 1 to 3, the total cost is here 0 plus 5, but the cost is 3. If you compare 5 with 3, 3 is minimum, so there is no change exist here. 1 to 4, if you consider 1 to 4 path, 0 plus 5, compare 5 with 5, both are say equal, so there is no change occurs here. Next 2 to 5 path you can consider. If you consider the path from 2 to 5, the total cost is 3 minus 1, that is equal to 2. 2 is less than 5, hence 5 is replaced with the 2. Next 3 to 2, path from 3 to 2, you can consider is, so the cost is 3. 3 minus 2, 1 we will get. 3 minus 2 you will get 1, but 1 compared with 3, 1 is smaller, so 3 is replaced with 1. Next 3 to 5 you can consider. If you consider 3 to 5 here, we consider 3 to 5 here, and again you can apply the same relaxation formula. The cost is 3 to 5. The cost is 3 minus 3 or 2. The cost is 3 to 2, no? 3 to 5. 3 to 5. If you observe, the cost is 3 plus 1, 4. But 4 is greater than 2. 4 is greater than 2. But always we need to consider the minimum value. That's why consider 2 only. No change occurs. 4 to 3. 4 to 3. Yeah. Sorry. 4 to 3. 4 to 3. If you consider here, the total cost is 5 minus 2. 3 here, both are same, no changes occurred. 4 to 6. 4 to 6, any change is there. 5 minus 1, 4. Here 4, both are same, no change occurs. 5 to 7. 5 to 7, 2 plus 3, 5. 5 compared with 7, this is small, so it is replaced with 5. 6 to 7. 6 to 7, 4 plus 3, 7. 7 compared with 5. 5 is small, so no change is occurred. So here this seems to be second cycle also over. In the second cycle, if you apply the same, if you apply all the edges to the given graph, so after end of pass 1, we will get in this way. So this is called as a pass 2. This is called as a pass 2. Now we will see how pass 2 will be generated. We will see this in this one. Pass 2. So friends, in this pass, we clearly observed that there are many changes occurred in the pass 2. Now we can once again apply the same edges to the given graph. When we apply the same to the given graph, after end of pass 2, clearly observe that 1 to 2, 1 to 2, the cost is 0 plus 6, 6. Compare 6 with 1, 1 is small, so no change. 1 to 3, 1 to 3, 0 plus 5, 5 compared with 3, 3 is minimum, so no change occurs. 1 to 4, 1 to 4, 5 compared with 5, both are same, no change. 2 to 5, 2 to 5 here, 1 minus 1, 0. So the path from 2 to 5 changed, 1 minus 1, 0. So 2 is replaced by 0. Next 3 to 2. 3 to the 3 cost is 3 minus 2, 1. Here 1, both are same. No minimum, no change occurs. 3 to 5. Compare 3 with 3 to 5. Now the path from 3 to 5 is 3 plus 1, 4. 4 is greater than 0. So ignore it. No change occurs. 4 to 3. 4 to 3. 5 minus 2, 3. 3 compared with 3. Both are equal. No change occurs. 4 to 6. 4 to 6. 5 minus 1, 4. Both are same. No change occurs. 5 to 7. 5 to 7. 0 plus 3. 0 plus 3. 3. 3 compared with 5. 3 is minimum. Always consider the minimum value. Change is made here. Next 6 to 7. 6 to 7. 4 plus 3, 7. 7 compared with 3. 3 is small. No change occurs. So this is the path 3. In the path 3, two edges in the at the end of path 3, two more changes occurs. 0 and 3. Next, we will see end of path 3 value. And the end of path 3, these are the changes occurs. Now we will apply once again we will apply the same concept here. Once again we will apply so now we are in the we are completed 3 process as of now. We have been completed pass 1, pass 2, pass 3. Now we will apply a relaxation formula to the given graph once again. So 1 to 2, any changes occurs we will see. 1 to 2, 0 plus 6, 6 compare with 1. So 1 is minimum, no change occurs. 1 to 3, 1 to 3, 5. 5 is 3, 3 is minimum, no change occur. 1 to 4, 1 to 4 if you observe, 0 plus 5, 5 compare with 5, both are same, no change occurs. 2 to 5, 2 to 5, 1 minus 1, 0. Here already 0 is there, no changes occur. Next 3 to 2, 3 to 2, 3 minus 2, 1, already 1 is there, no changes occurs. 3 to 5, next 3 to 5. If you consider 3 to 5, 3 plus 1, 4, 4 compare with 3, 4 compare with 0, 0 is minimum, no change occurs. 4 to 3, 4 to 3, 5 minus 2, 3. 3 compare with 3, no change, done. So consider no change is applicable. 4 to 6, 4 to 6, 5 minus 1, 4 compare with 4, both are equal, no changes occurs. 6 to 7 next. 6 to 7, 4 plus 3, 7, 7 compare with 3, 3 is minimum, no change is occurs. So here, no change, no changes are made here, no changes are made here. So no changes are done here from pass 3 to pass 4. Hence, we need to stop the process. We need to stop the process here. Why we need to stop the process here? There is no further changes are identified from vertex 1 to vertex 2, vertex 1 to vertex 3. So from all the edge lists, no changes are made. Hence, we are literally stopping further, no more changes are to be done here. Once this is occurred, then what the next step is, what we will do is, the next step is, I will explain the next step is, you need to find the path from one node to another node clearly. So now find the path of, now find the distance of node 1. The distance of node 1 is 0. The distance of node 2, what is the distance of node 2? The distance of node 2 is 1. 1 is clearly mentioned. What is the distance of, minimum distance of node 3? The minimum distance of node 3 is 3. 3. The minimum distance of node 4. Node 4 minimum distance is 5. Node 5 minimum distance is, node 5 minimum distance is 0. Node 6 minimum distance is 4. Node 6 minimum distance is 4. Node 7 minimum distance is 7. Node 7 minimum distance is 3. Node 7 minimum distance is 3. This means that, so here this is the minimum distance and this is the node minimum distance from one node. Now, if you want to find, these are the, find the minimum distance from 1 to 4. I want to know the minimum distance from one path to another path. If I want to know the minimum cost or minimum shortest path from node 1 to node 4, node 1 here and this is node 4. So what is the total cost is 5. How we will see 1 to 4. So 1 to 4, how we will go for 1 to 4? First, 1 to 4, if you want to move 1 to 2, it will cost is 1. Here it will cost is 1. Then from 2 to 3, you will move. You will move from 2 to 3. There is no way from moving from 2 to 3. So hence, you move to 1 to 4. If you want to move from 1 to 4, directly it is 5. Sorry. If you want to find the cost from 1 to 4, if you want to find the cost from 1 to 4, is a path exists that is called directly 5. If you want to find the cost from, if you want to find the cost from 1 to 5, 1 to 5. If you want to find the minimum cost from vertex 1 to vertex 5. Now we will see how to do. Vertex 1 to vertex 5, minimum cost is 0. How we will see. If you want to move from vertex 1 to vertex 5, how we will see. Okay. Here, first, initially you need to move from 1 to 2. Then you need to move from 2 to 5. If you want to reach from 1 to 5, you can move from 1 to 2 first. Move from 1 to 2 first. Then from 2 to you can move 5. Then 2 to you can move to 5. So what is the distance from 1 to 2? The distance from 1 to 2 is 1. The distance from 1 to 2 is 1. And the distance from 2 to 5 is 0. Is minus 1. Distance from 2 to this one is minus 1. So total distance is 1 minus 1, that is equal to 0. And the total distance from vertex 1 to vertex 5 is 0. The total distance from vertex 1 to vertex 5 is 0. Friends, in this way, we need to solve the problem very easily by using Bellman Ford algorithm. Okay, I hope you understood this very well. So you need to start here, then only you will get the final answer. Okay. So once again, I will explain the concept. This is the given graph. In the given graph, first apply relaxation property. Then you can consider what are the possible ways of generating the edges from the given graph. Based on the directions, you can generate the edges. Once the edges are generated, then start consider the weight of first edge is 0. The remaining vertex weights you can consider as infinity, all edges. Once 0 and infinity are, you can assign as a cost to the all vertices, then apply comparing the edges, all the edges one by one. You can apply from 1 to 1 3 1 4 till 6 7. So always you need to find the minimum cost each and every point of view till the end of the process. So once the full cycle is completed, you can reach the end of the pass one. Once reach end of the pass one, again you can apply the same concept with the following edges. Apply the same thing. Then you need to begin pass two. We can apply the same concept and we will get the pass two values. At the end of the pass two, full cycle once again two times if you complete it, you will get this result. And again we can begin pass three. So once pass three is begin, apply the same concept to the given graph, and we will get the end of pass three. And there is no changes applicable for end of pass 4 also. Once there are no changes are made for end of pass 3 or pass 4, you need to simply stop the process of doing the process. Once you stop the process, then you can find the minimum edge of the minimum cost of all the vertices, starting from vertex 1, 2, 3, 4, 5, 6, 7. You can find all these that can be considered as the minimum cost path from source to destination. So in this way, we can find the value. Okay, I hope you understood the concept, and we will discuss the same problem with another example in the next class. I hope you understood this very well. Thank you. Thank you, Meera.